Hello everyone. Today we are going to discuss capacitance of parallel plate capacitor. That is, we are going to find mathematical expression for capacitance of parallel plate capacitor. In order to find capacitance of capacitor, we use the concept of Gauss law and potential difference. Let us understand Gauss law and potential difference in brief. This is the mathematical statement of Gauss law. Okay, it states that surface integral of electric field, because this is area vector, okay, throughout the closed surface equals 1 by epsilon 0 times the charge enclosed by that closed surface. And potential difference can be written as Vf minus Vi, where I and F indicates initial and final position, and Vf is the potential at final position, and Vi is the potential at initial position. So this difference gives the potential difference between initial and final position equals negative and integration from initial to final position. Okay, and we have vector E dot displacement. Okay, so this is displacement. So this is the expression for potential difference. So I will be coming to this expression later. Now let us consider two metallic plate, okay, separated by small distance d, and let us assume free space or vacuum between these two plates. And if we consider free space, and for free space we take permittivity, that is epsilon 0. Okay, now let the upper plate be positively charged and the negative lower plate contains equal amount of negative charges. So we have two plates containing equal amount of positive and negative charges separated by small distance. So sometime, let us understand in general, okay, sometime we tell the charge on capacitor is Q. So what does it indicate? The charge on capacitor is the charge on positively charged plate. So we need to note this, okay? So the charge on capacitor is the charge on positive plate of the capacitor. So here we have two plates containing equal amount of positive and negative charge. So this system is called parallel plate capacitor, and we have free space or vacuum between these two plates. And for vacuum we use or we take permittivity of free space, that is epsilon 0 or epsilon naught. Now what happens if the distance between the plates is large? So suppose we have two plates, okay, containing equal amount of positive and negative charge, and if the distance is large, then electric field lines at the edge fringes out. So we can see electric field lines starting from positive plate are not terminating on negative plate. So this kind of effect is called A's effect. And electric field is not uniform between these two plates. So we must note it. Clear? Now, this A's effect is minimized by taking two plates at small distance. Clear? So we are having distance between these two plates small. Now, as I said earlier, the upper plate contains positive charge and the lower plate contains negative charge. We find electric field between these two plates. So electric field lines start from positive plate and terminates on negative plate. So electric field lines start from positive plate and terminates on negative plates. Okay, so electric field lines start from positive plate and terminates on negative plate. So electric field is directed from positive to negative plate, and we can see electric field lines are parallel to each other. Now, electric field between these two plates is constant or is uniform. So for that reason, electric field lines are equally spaced. So we must note this also. Clear? Now let us use Gauss law. Okay. So we are using Gauss law. Now we want to use a Gauss law. In order to use Gauss law, we must draw Gaussian surface. So this is a Gaussian surface, okay, and it encloses all the charges on this plate. So this is a Gaussian surface, and let us assume area of each plates is A, that is capital A. Okay, now the Gaussian surface contains charge. So we find electric field lines, okay, are leaving positive plate normally and are entering or terminating negative plate normally. Okay, so we find this. Now let us take small elemental area of the Gaussian surface. So we are taking small elemental area of a Gaussian surface, okay, and let's its magnitude be dA. Now since the electric field lines is crossing normal, okay, is falling normally or is crossing normally through this area, let us draw a unit normal n cap, and this unit normal gives the direction of vector area. Okay, this gives the direction of vector area. So we find electric field and vector area, they are acting along same direction. So the angle between dA, that is vector area dA, and electric field is 0 degree. Clear? So we need to understand this. So Gauss law, it relates the electric field E in this case, okay, between the plates with either charge Q on the plates. So we can write in this way, okay. So we have this. So this is an elemental area of the Gaussian surface. Now, as I said earlier, electric field and area vector, they are acting along same direction. So the angle between them is 0 degree. So for that reason, we can write EDA cos 0 degree. Okay, and we have integration throughout the closed surface. Okay, we have a closed Gaussian surface. So this equals Q by epsilon 0. Now cos 0 is 1. And as I said earlier, electric field is uniform or is constant between these two plates. So we can take electric field out of the integral. So we have this. Now, if we integrate, okay, throughout the closed surface, because dA is a part of Gaussian surface. And if we integrate throughout the Gaussian surface, suppose this is a Gaussian surface, okay, because dA is a elemental area or is a small area of a Gaussian surface. Now, if we integrate throughout the Gaussian surface, then we get total area of a Gaussian surface. So this gives us area of Gaussian surface through which the flux is passing. We take that part of the Gaussian surface through which electric flux is passing, or we take that part of the Gaussian surface which encloses electric charge, and this equals area of plate. So area of plate is capital A. So finally we can write this integral equals A, capital A. So we have EA equals Q by epsilon 0. So electric field between these two plates equals Q by epsilon 0 A. So we must note that we are taking that part of the Gaussian surface through which electric flux is passing, or we are taking that part of the Gaussian surface which contains electric charge. And since electric charge is present on this plate, okay, and the plate is having area capital A, so this integral gives the value capital A. And this expression can be derived in this way. We know electric field equals surface charge density, okay, by epsilon 0. So this is surface charge density and its value is Q by A. So we can write E equals Q by epsilon 0 A. So we can find the electric field in this way, okay. Now, let us use the concept of potential difference, okay. So let me redraw this figure again, okay. Upper plate contains positive charge and lower plate contains equal amount of negative charge, okay. We have this, and if we integrate from lower plate to upper plate, that is, if we integrate from negatively charged plate to positively charged plate, that is the direction of integration, okay. This is the direction of integration. Suppose we want to integrate from negative to positive plate, that is, this is the direction of integration, okay. This is the direction of integration. Then this expression can be rewritten as Vf minus Vi equals minus integration from initial to final. Okay, now we want to integrate from this position, okay, to this position. So this is the initial position and this becomes the final position. Now we know electric field lines is directed along this direction, and this is displacement. We want to integrate along this direction. So we find electric field and displacement, they are oppositely directed. So in this case, we can write EDL, and the angle between them is 180 degree. Okay. So we have this clear, because electric field and displacement are oppositely directed. So the angle between vector E and vector DL is 180 degree. And this gives us Vf minus Vi. So let me write this in this way, okay. Potential difference V equals, so cos 180 degree, this is -1. So we get integration from initial to final, okay, E dl. So we have this, and we can write this relation in this way, okay. Initial with reference to this figure, okay. Initial is, we are starting from negative plate, so negative to positive, okay. So the lower limit is negative and the upper limit is positive. That is from negative plate to positive plate, E dl. So this is the expression for potential difference. So we are going to use this relation. So let me erase this, okay. We are going to use potential difference PD. So let us denote it by symbol V equals integration from negative plate to positive plate, E dl. So we have this, okay. So I'm writing this in a row. Okay. Now the potential difference. So in this expression, we see the potential difference is related to electric field. Okay. The potential difference between the plates is related to electric field by V equals integration from negative plate to positive plate, E dl, and we have electric field, okay. So we can write in this way. So E is Q by epsilon 0 A. So I'm going to put the limit later. Okay. And we have DL. Now we are integrating from negative plate to positive plate. Okay. So let me erase this also. So we are integrating from this position. This is the initial position to this position, final position. Okay. So we want to integrate along this direction. So the lower limit is 0 at this position. Okay. And finally, when we reach from this position to this position, okay, then the distance is D. Clear? So the upper limit is D, because at this position we have 0 as the lower limit, and finally when we reach to upper plate, then we have upper limit, that is small d. Now we can write V equals Q by epsilon 0 and integration from 0 to D dl, because Q is constant, epsilon 0 is constant, because we are taking free space or vacuum between the plates, and A is constant. Now if we integrate this, okay, from this position to this position, then we get the total distance between these two plates. So this integral finally gives the value D. So we can write potential difference between the plates V equals Q D by epsilon 0 A. So this is equation number 2. Now we know for capacitor, Q equals CV, and C is called the capacitance of capacitor. So we can write C equals Q by V. So let us call it equation 3. Now from 2 and 3, okay, we can write C equals Q divided by V, and V is QD by epsilon 0 A. So we can write in this way, Q epsilon 0 A by QD. So QQ cancel. So finally, we can write capacitance C equals epsilon 0 A by D. So if we have free space or vacuum between the plates, okay, then for such parallel plate capacitor, C is directly proportional to area, and C is inversely proportional to the distance between the two plates. So capacitance depends on geometrical factors, that is area of the plate and distance between the two plates.